Welcome back, sleepy traveler, to this quiet corner of the cosmos, where we stretch out the universe one gentle thought at a time. Tonight we'll drift together into a question that's both simple and staggeringly vast. Where does space actually end? It sounds like the kind of thing a child might ask on a starry night, innocent and almost playful. Yet the deeper you sink into it, the more it unravels your sense of reality. It's the kind of puzzle that stretches the imagination the way the universe stretches itself, endlessly, softly, and without clear boundaries. This is meant to be a calm journey, one you don't need to stay fully awake for. Let it carry you off to sleep, if that's what you need. But if curiosity keeps you listening a little longer, at least you'll come away with a pocket full of wonder, a few cosmic secrets to hold on to. Before we lift off together into that vast blackness, I'd love for you to leave a trace of your presence here, perhaps a like or a quiet little subscription if you haven't done so already. Every bit of support helps this sleepy little channel find others like you, scattered across time zones and beds and couches all over the world. Wherever you are listening from, whether it's a dimly lit apartment in Stockholm late at night, or an afternoon couch in Melbourne with the sun spilling through the blinds, I imagine you're part of a community of wanderers scattered gently across the globe. Each of us looking upward, each of us pausing to ask what lies beyond. So, settle in, let yourself breathe more slowly, and allow your thoughts to drift like dust motes in a shaft of light. You don't need to memorize anything or keep your eyes wide open. Just let the words ripple through your mind like background radiation, soft, steady, ever-present. And now, let's begin. What is space, really? That silent black backdrop against which every star gleams, every galaxy swirls, every comet races past. At first glance, it feels like nothing at all, a void, an emptiness, a canvas without paint, a place where planets and suns are scattered like flecks of dust, where socks lost in the dryer might drift off to retire. But what we call nothing is far from empty. Space, it turns out, is alive, humming quietly with activity and mystery, rich with structure even in its darkest corners. For centuries, humans thought differently. They imagined space as a stage, something static and unchanging, a wooden floor on which the actors, stars, moons, planets played out their scenes. This was the world of Isaac Newton, who believed in absolute space, an arena fixed forever, unmoving, with time ticking steadily in the same rhythm for everyone, everywhere. It was a comforting picture, simple and orderly. And then along came Albert Einstein, with his wild halo of hair and chalkboards scrawled with equations like half-forgotten dreams. Einstein toppled Newton's neat model and replaced it with something far stranger and far more elegant. According to him, space isn't just a background. It's a living, stretching fabric, one that bends and curves, twists and ripples, depending on the weight of the matter and energy it carries. Space and time, once thought to be separate, are stitched together into a four-dimensional quilt we call space-time. And space-time doesn't just sit idly by, it responds. To imagine it, think of a trampoline. Drop a heavy bowling ball in the center, and the fabric dips, sagging under the weight. Now roll a marble across it. The marble won't move in a straight line. Instead, it curves, spiraling toward the dip. That is gravity in Einstein's world. Not some invisible magnet tugging us down, but the curve of space-time itself guiding our path. Earth bends space-time around it, and we, like marbles on that stretched trampoline, are drawn inward. At this point, You might shrug and say, fine, so space can bend. But what about the empty stretches between stars and galaxies? Isn't that truly nothing? Not quite. Quantum mechanics has revealed that even in the loneliest corners, space is anything but empty. At scales far smaller than atoms, space fizzes with energy. It shimmers with quantum fields, fields that aren't just things floating in space, but space itself woven into invisible frameworks. Every particle in existence arises from these fields. The electron field gives us electrons. The photon field gives us photons. They're like hidden seas, and particles are the ripples on their surface. Even when no particles appear, these fields never fall silent. They fluctuate constantly, bubbling up tiny flashes of energy, spawning virtual particles that wink into being and vanish in an instant, like cosmic fireflies flickering in a night meadow. This restless libration is called vacuum energy, and it's everywhere. From a distance, the vacuum may look like a still pond, but lean in close, and you see ripples, disturbances, sudden flickers of life. Physicists can't catch these ghostly particles directly, but they can measure their fingerprints. These fluctuations subtly shift how electrons behave, shaping the tiny dance around an atom's nucleus. They might even contribute to dark energy, the strange and invisible force that is driving the expansion of the universe ever faster. So no, space is not a passive emptiness. It is a restless, shimmering fabric, alive with possibility, pregnant with potential. It bends, it stretches, it ripples with energy. It has a faint warmth left over from the birth of the cosmos, just a few degrees above absolute zero. Even the void between galaxies is faintly glowing, faintly alive, with relic heat from the Big Bang itself. And that is the strange comfort of it. What we call nothing is never truly nothing. Even in the quietest moments, even in the darkest voids, there is always motion, always hum, always the flicker of possibility. Space itself is one of the characters in the story of existence, not merely the stage on which the play unfolds. It isn't where things happen. It is one of the things happening. Now imagine standing on a quiet hilltop at night, the stars stretched in every direction, the air cool and still. You feel as though the universe goes on forever. But the truth is subtler. There is a boundary to what you can see. Not because the universe ends there, but because light itself has only had so much time to travel since the beginning. That boundary is what we call the observable universe, a vast bubble around us defined not by walls but by time. Inside it lies every photon, every gravitational wave, every signal that has managed to arrive since the universe began. Beyond it lies, we cannot say. At first you might assume the edge of visibility is 13.8 billion light-years away, since that's roughly the age of the universe. But space has a trick up its sleeve. Because it has been stretching the whole time, the actual radius of the observable universe is about 46.5 billion light-years. That makes the bubble across about 93 billion light-years in diameter. Enormous, almost absurd. The universe is 13.8 billion years old, but the farthest galaxies we can see are more than 3 times farther than that, because the fabric of space has been expanding under their light as it traveled. Think again of bread rising in the oven, raisins scattered across the dough. As the dough swells, the raisins drift farther apart. Imagine a tiny photon leaping from one raisin toward another at the very start of the baking. By the time it arrives, the bread has stretched, and the raisins are much farther apart. That's what happens on the cosmic scale, light crossing not a fixed distance, but a distance that grows as it travels. This gives us the cosmic horizon. Don't picture a brick wall or a sharp edge. Imagine instead standing in fog, able to see a soft glow nearby. But beyond that, nothing. Not because it isn't there, but because the light hasn't reached you yet. Beyond the horizon, the universe continues, but its messages haven't arrived. And the horizon isn't still. It shifts as time flows. New light from farther regions trickles in, expanding our bubble. But at the same time, space itself is expanding so fast that some galaxies will forever outrun us. Their light, emitted now, will never reach Earth, not even after trillions of years. It's not that they are racing faster than light in a forbidden way. It's that the fabric between us is stretching too quickly. That thought is both humbling and strangely peaceful. Every star you've ever seen, every galaxy in the night sky, fits within this glowing bubble of observability. And yet beyond it almost certainly lies far, far more, perhaps infinitely more. Worlds, galaxies, structures, and mysteries we will never touch. Even more humbling, every place in the universe has its own observable bubble. Someone on a galaxy 10 billion light-years away would see a partly overlapping horizon, different from ours, but theirs would also include regions we can never know. The observable universe is not the universe. It is only our slice, our perspective, one glowing fragment of a much vaster whole. And what a slice it is! Roughly 2 trillion galaxies, each with millions or trillions of stars, all stitched into this fragile sphere of light we can see. Photons that began their journeys before Earth even formed are only now touching the back of your eyes or the mirrors of a telescope orbiting far above. The light you see tonight might have been born when the universe was young, when there were no oceans on Earth, no life stirring in the waters, only gas and gravity and time. That ancient light is a message in a bottle from a past so distant it almost doesn't feel real, and yet it touches you now, in this moment. But as enormous as this bubble is, it is only the frosting on the cake. Beyond it, space may go on forever, or it may curve back on itself in dimensions we cannot imagine. Maybe it stretches into infinity. Maybe it folds into a loop. We cannot know. The laws of physics put a veil over that part of the story, and no signal bound by time or causality can pierce it. And there is something almost comforting about that too, the reminder that we don't need to know it all. We don't need to hold the entire cosmos in our minds to find meaning. Sometimes it's enough to sit under the stars and feel that we are part of something vast beyond measure. When we gaze up at the night sky, it's tempting to believe we're looking at the universe as it is right now. But that's an illusion. Every point of light is really a memory. Each star and galaxy you see is a time capsule, sending out ancient news, some of it so old that it predates Earth itself. Light doesn't arrive instantly. It has to travel, and that journey takes time. Which means every glittering spark is a story from long ago, not a reflection of the present. To put it in simple terms, think of the light year. A light year is not a measure of time, but of distance. The distance light can travel in 1 year, nearly 6 trillion miles, about 10 trillion kilometers. If you spot a star 100 light years away, the photons hitting your eyes tonight left that star when your great-grandparents were young, carrying with them the star's past, not its present. Stretch that idea across the unfathomable gulf of space. Some galaxies we observe lie billions of light years away. The glow we see from them began its voyage before Earth had oceans, before its crust had cooled, before even the earliest whispers of life stirred in its waters. The light you catch tonight may have been racing toward you for 10 billion years, just waiting for your gaze to complete its journey. Astronomers call this concept look-back time, the measure of how far into the past you're peering when you observe distant objects. A galaxy 8 billion light-years away offers us an 8 billion-year-old snapshot. Its light began moving long before humans, before dinosaurs, before the continents as we know them existed. In this way, the universe becomes a vast museum, and each patch of sky is a gallery filled with fossils made of light. And those fossils tell strange stories. We are not seeing galaxies as they are today. We are seeing them as they were long ago, frozen in earlier chapters of their existence. Some of them may no longer exist at all. They could have merged with neighbors, transformed into new shapes, consumed their fuel, or drifted forever beyond our horizon as space itself expanded. What we see is not a live performance, but a record, a fossilized glow written across space-time. As light travels, it doesn't remain unchanged. The universe plays with it. Because space is expanding, light stretches too. Its wavelength grows longer, shifting toward the red part of the spectrum. Astronomers call this redshift, a cosmic echo of the Doppler effect, the same reason the wail of a siren drops in pitch as an ambulance speeds away from you. Nearly all distant galaxies show this redshift, proof that they are receding from us, pulled along by the swelling fabric of space. Redshift is more than a curiosity. It's a ruler. By measuring the degree of stretching, astronomers can estimate how far a galaxy lies and how long its light has been traveling. A high redshift points to an ancient glimpse, a window into the young universe itself. Every redshifted photon is a message carrying secrets, the pace of expansion, the composition of matter, the invisible tug of dark energy. Telescopes become our time machines in this story. A backyard telescope shows you Jupiter as it looked about 40 minutes ago, the time it takes light to cross the gulf between us. A large observatory might reveal a galaxy as it appeared 500 million years in the past, when life on Earth was still confined to the seas. The Hubble Space Telescope, the James Webb Space Telescope, and their successors stretch this ability further, peering so far that they capture the faint glow of the very first galaxies, born just a few 100 million years after the Big Bang. Imagine staring across a vast abyss and seeing the first sparks of cosmic dawn flicker into being. That's what modern astronomy offers, a window not just into space, but into history itself. It's almost ironic. To understand where the universe is going, we must spend most of our time looking backward. Light travels unimaginably fast, but the distances are greater still, and so the story always reaches us late. In a sense, we're always out of sync with the universe, watching scenes long after they've been acted. It's like arriving at a theater after the curtain has dropped, but still catching the echoes of dialogue through the walls. And yet, this delay is a blessing. Without it, we'd never be able to reconstruct the past, to glimpse the stages of cosmic evolution all at once. Each star, each galaxy is like a torn page from a novel scattered across the sky. One page may show a galaxy in its infancy, another may reveal a mature spiral with billions of stars, and yet another may capture a faint smudge from an age when the cosmos was still dim and new. Together they form a mosaic, a patchwork quilt of time stitched together by light. Think about what that means. When you look in one direction, you might see a galaxy born only a few billion years ago, still young and bright. In another direction, you may be catching the faint glimmer of primordial galaxies from the very dawn of time. You are surrounded by layers upon layers of history, each photon a relic, each shimmer a messenger carrying tales older than the earth beneath your feet. This is why some scientists describe the cosmos as a museum of ghosts. The stars twinkling above you may already have died, their light just now completing its journey. The galaxies you admire may have merged, faded, or transformed beyond recognition. You are not looking at what is, but at what was. Every glance upward is an act of time travel, a communion with ghosts of the past, and in that sense, space is full of echoes, silent, colorful echoes that whisper about the expansion of the cosmos, the birth of stars, the death of suns, the merging of galaxies. All of it encoded in wavelengths, in patterns of light that scientists learn to decode. By listening to the language of light, they unlock the story of creation itself. Pause for a moment to imagine that. Each twinkle, each distant gleam is a letter in a book being written across billions of years. And we, small creatures on a small planet orbiting a modest star, are learning to read it. We are piecing together the novel of existence one photon at a time. And while the observable universe is vast, so vast that its diameter stretches 93 billion light-years, it is still just our bubble, our local view. Beyond it lies more, perhaps infinitely more. Galaxies without number, structures beyond our wildest theories, maybe even entire realms where the physics plays by slightly different rules. And we will never see them. Not because we lack the technology, but because the universe itself refuses to deliver their light to us. That limitation can feel humbling. Some may even find it frustrating. But there's peace in it too. To know that our perspective is local, bounded, finite, makes our experience precious. You don't need to see it all. You don't need to command the entire cosmos. It's enough to sit beneath your own night sky. Look up at the stars in your slice of universe and feel that you belong. And belonging doesn't require infinity. It requires only connection. Every atom in your body is tied to the fabric of space-time. Every breath you take is bound up in the same cosmic dance that bends galaxies and shapes horizons. You are not outside of the story. You are written into it. So when we ask whether space ends, whether it has boundaries, we may be missing the point. Space is not a container that holds us. It is the story itself unfolding. It twists, it stretches, it hums with unseen motion. It glows faintly with the afterlight of the Big Bang. It expands, carrying galaxies with it, even as it hides others, forever beyond our reach. Even when it seems to do nothing, space is never still. It is restless. It is alive. And perhaps the strangest truth of all is this: the more we learn about space, the less it resembles emptiness. The more we study it, the more it resists the idea of void. What we once called nothing has become everything: fields, energy, geometry, potential, horizons, echoes of the past, and whispers of a future still unfolding. And maybe, just maybe, that's the true gift of space. It doesn't end with answers. It expands with questions. Questions that keep us awake on quiet nights, staring upward. Questions that stretch our minds as they stretch the universe. Where does it end? Does it end? Or does it continue forever, like a song with no final note? For now, the only certainty is this: we live inside a bubble of light, a fragile globe of information carved by photons and time. It is not a prison, but a gift that grows slowly, giving us more to see, more to wonder at, more to dream about. And in this gentle truth, we find comfort. We don't need to reach the edge of the universe to feel infinite. The infinite is already here, woven into the night sky, reflected in every gleam, every ghost, every ripple in the fabric of space. So as you drift off tonight, remember this. You are floating inside a vast, luminous bubble, drifting through an endless story, a story without walls, a story that refuses to stop. And in that story, your thoughts, your breath, your heartbeat are part of the cosmic hum. Close your eyes, let the stars settle above you like a blanket, and let yourself rest in the quiet knowledge that space may never end, and neither will the wonder it inspires. That light we catch from the distant past, the fossil record written in photons, becomes even more fascinating the closer you listen to it. Because light does not simply carry a picture, it changes on the way. As it crosses the expanding fabric of the universe, it stretches. That stretching is what astronomers call redshift. Just as the sound of a siren lowers in pitch when an ambulance speeds away, so too does light change its tune when its source drifts from us. The faster it recedes, the longer its wavelength becomes, shifting toward the red end of the spectrum. And since space itself is expanding, nearly all distant galaxies are receding from us. Their light arrives not as it was first born, but stretched thin, softened, reddened by the swelling fabric of space-time. This reddening, simple to describe, carries with it profound meaning. By measuring just how much a galaxy's light is redshifted, astronomers can not only estimate its distance, but also determine how long that light has been on its voyage. A higher redshift is a deeper reach into antiquity, a chance to glimpse the universe as it was billions of years ago. In that sense, every photon that reaches us is more than a dot of color. It is a messenger. Encoded in its stretched-out waves are hints about the universe's age, its rate of growth, the hidden currents of dark energy shaping its destiny. Each photon is like a letter written in the alphabet of light, sent across billions of years to reach our retinas or our detectors. Read carefully. They tell stories about how galaxies were born, how stars first ignited, how gravity and dark energy have been locked in a tug-of-war since time began. This is why telescopes are not just tools for looking farther. They are instruments for looking deeper into time. A backyard telescope, modest though it is, already turns you into a kind of time traveler. When you peer at Jupiter's swirling storms, you're not seeing them as they are in that exact moment, but as they were roughly 40 minutes earlier, the time it takes for light to bridge the gap between Earth and Jupiter. Look through a more powerful observatory, and suddenly you are staring at galaxies as they were 500 million years ago, when life on Earth had only begun to explore the seas with fins and gills. And then there are the giants, Hubble, James Webb, and the observatories that will someday follow them. These are the deep-sea divers of the cosmos, plunging not into oceans, but into time itself. They can capture the faintest embers from the first galaxies, fragile structures that began assembling just a few 100 million years after the Big Bang. Imagine that, a telescope on a small planet orbiting a modest star, catching photons that have traveled for almost the entire history of existence. Photons that began their journey before the first tree grew on Earth, before Earth even existed at all. It is a little ironic, isn't it, that in order to learn where the universe might be heading, we must spend most of our effort looking backward. Light is fast, but the universe is large, and so the cosmos as we see it is always slightly out of date. You are never looking at the present sky, only at an archive of moments already gone. In that sense, Our universe is like a film being delivered one frame at a time, sometimes out of sequence. This frame from a galaxy next door, this one from a quasar 10 billion years away. It is a collage of time stitched together into a sky. That delay, far from being frustrating, is a gift. Without it, we would never be able to trace the story of how things came to be. The slow arrival of light lets us hold snapshots from every era of cosmic history, all at once, scattered across the heavens. One patch of sky might show a galaxy just recently formed. Another might reveal a flickering signal from 1 billion years after the universe began. And another might glow with starlight so young it's barely distinguishable from the cosmic background. Each direction is a page torn from a novel and tossed into the air. Collect enough of them, and you begin to piece together the plot. It's as though we live in a museum, not of stone and glass, but of light. Every night, the exhibits come to us, carried across incomprehensible distances. You don't need to walk from hall to hall. The photons arrive on their own schedule, whispering the history of galaxies, of stars, of the universe itself. The dome of the sky becomes the museum ceiling, and each star, each faint smear, each shimmering dot is an artifact on display. There is something quietly poetic in this arrangement. To look up at the night sky is to place yourself inside a time machine. Every glance is a journey backward. That star shining faintly above you may have begun its journey before the first forests on Earth. That galaxy's faint light may have set out long before the Earth had oceans. The photons that brush your eyes tonight are survivors of an impossible journey, ancient messengers finally arriving to complete their story. And what makes all this possible is our ability to listen to light, not just to see it, but to decode its subtleties, its color, its stretch, its age. Each tells a part of the tale. Light doesn't just describe the universe. In a very real sense, it is the universe, encoded in wave and particle, motion and memory. To study light is to study existence itself, to read the most ancient record ever written. So the next time you see a star twinkling above, pause to consider. You are not looking at it as it is. You are looking at a memory preserved in motion, a glimmer of history still on its way. You are catching the universe mid-sentence, overhearing a whisper from the past. And through this patient stream of light, through this endless library of photons, we slowly reconstruct the story of where we came from and how everything around us unfolded. Picture yourself not beneath a night sky now, but in a quiet meadow at dawn. The grass sparkles with dew. A thin fog drapes itself across the horizon. You can see the closest trees, perhaps the outline of a hill in the distance. But beyond that, the world vanishes into mist. You know it continues, forests, mountains, cities, but your sight is hemmed in by the haze. This is what it means to live in the universe. No matter how powerful our instruments, there is always a horizon, a place beyond which vision fails. But unlike the fog on Earth, our horizons are not made of water droplets. They are made of time and distance, of the expansion of space itself. They are called cosmic horizons, and they mark the true boundaries of what we can observe. These horizons don't wall off reality. They merely remind us how far light has had time to travel since the universe began, and how much of the cosmos has slipped away faster than light can deliver its messages. The first is the particle horizon, the ultimate edge of the observable universe. It represents the farthest distance from which any signal, whether photon or gravitational wave, could have reached us since time began. It is not a wall. It is a gentle limit woven into the age of the cosmos itself. The universe has existed for about 13.8 billion years. Space has been expanding all the while. The result is that the maximum distance light has had time to cross is about 46 billion light years. In every direction, This radius defines our cosmic bubble. The full span of it, from one side to the other, is about 93 billion light-years, a vast but finite sphere enclosing all that we can currently observe. Yet standing at that limit, you would see nothing resembling a border. There is no glowing rim, no cosmic fence post with a sign that reads "End of Universe." Instead, it's more like standing at the shore of an endless sea. You look as far as the light allows, but beyond that curve, the signals simply have not arrived. The universe is not finished there. It continues. It's just that its voice has not yet reached us. Beyond the particle horizon lies another boundary, quieter, but perhaps even stranger, the event horizon of the universe. When most people hear event horizon, they picture a black hole, that inescapable line where gravity holds light itself hostage. But in cosmology, the event horizon takes on a different meaning. It is the line beyond which no event, no burst of light, no signal of any kind will ever reach us, no matter how much time passes. Imagine a friend drifting down a river on a raft. You toss messages in bottles, hoping they'll float to her. But the current is too strong. The raft glides faster than the bottles can travel. So no matter how many notes you throw, none will arrive. That is the event horizon of the universe. Anything beyond it is being carried away from us faster than light by the swelling fabric of space. Their signals, however faithfully sent, will never arrive. Right now, scientists estimate that this cosmic event horizon lies about 16 billion light-years away. This means there are galaxies we can see today because their ancient light is still arriving. But any new light they emit from this moment onward will never make the journey. In a sense, we're watching ghosts in real time, objects visible in our sky now, but destined to fade forever, their voices stretched beyond audibility, their glow swallowed by expansion. There is also what cosmologists sometimes call the cosmological horizon, a broader term that captures the shifting nature of these boundaries. Horizons are not static, they change with time. The particle horizon grows as more ancient light finally completes its journey to us. The event horizon, meanwhile, makes its own grim progress, shrinking the pool of galaxies we can hope to hear from, as dark energy accelerates the stretching of space. Over time, the universe becomes more isolated, not because it is empty, but because it is slipping beyond reach. Think again of the balloon analogy, dots painted on its surface. As the balloon inflates, the dots drift apart. The ones nearest remain within sight. The ones farther away recede so quickly that no signal can cross the distance. This is the geometry of our expanding cosmos. It isn't cruel. It isn't even intentional. It is simply the way the fabric of space behaves. There is a kind of melancholy beauty in this. Horizons remind us of our limits. They say, you are not an all-seeing observer. Your vision is framed by time, by distance, by the strange properties of the very space that carries you. There will always be corners of the universe that remain unknowable, not hidden behind curtains waiting to be unveiled, but truly beyond reach. And yet, within the slice we can see, we have managed to learn so much. We've traced the faint patterns of galaxies stretched across the sky, mapped the fingerprints of the Big Bang itself in the glow of background radiation, and measured the rhythm of expansion in the way starlight shifts and stretches. The horizons do not stifle curiosity. They frame it. They remind us that science is not about having everything, but about discovering within the limits of what can be reached. Like fog burning off at dawn, every new discovery reveals more, even as we accept that some landscapes will always remain out of sight. And this is where the story of cosmic expansion begins to reshape everything we thought we knew. Not too long ago, in the early chapters of science, many believed the universe was steady and eternal. Stars shone, galaxies spun, and the cosmos seemed a quiet, changeless backdrop. That illusion shattered in the 1920s, when Edwin Hubble peered through his telescope and noticed a pattern. Galaxies, no matter where he looked, were redshifted. And not only that, the farther away they were, the faster they seemed to recede. This was not a coincidence. It was a law written into the sky. Space itself was expanding. Not galaxies darting away through a fixed void, not cosmic marbles flung outward from a central blast, but the very stage itself, growing larger, stretching, carrying its actors with it. The image that often helps is raisin bread in the oven. Imagine galaxies as raisins baked into the dough. As the dough rises, every raisin drifts farther from the others. No raisin is special. No raisin is at the center. The expansion is uniform, impartial, relentless. Each one looks around and sees all the others receding. And the truth is stranger still. There is no outer crust of the loaf, no place where the dough stops. Space is not swelling into something larger. It is the fabric itself lengthening. Distances between unbound objects growing as the cosmic measuring tape stretches. When Hubble first revealed this discovery, it was radical. Even Einstein, whose equations had quietly hinted at expansion, had resisted. He had added a correction term, the cosmological constant, to force his universe to stand still, thinking a static cosmos was the only possibility. When he later learned of Hubble's results, he called that addition his greatest blunder. And yet, with cosmic irony, that very idea would return decades later to help explain dark energy. But in Hubble's time, it meant something profound. If everything is expanding now, then everything must once have been closer together. Rewind the cosmic movie, and galaxies collapse inward, stars converge, matter and energy compress into a hot, dense origin point. What scientists came to call the Big Bang. The name itself is misleading. It wasn't an explosion in space, with debris flying outward from a center. It was the expansion of space everywhere at once. No blast radius, no epicenter. The Big Bang happened everywhere, simultaneously, including right where you are sitting now. And it hasn't stopped. Nearly 14 billion years later, the expansion continues, carrying galaxies apart, stretching their light, reshaping the sky. The farther away an object lies, the more redshifted its light becomes, stretched thinner and thinner by the fabric it crosses. The universe's expansion is a cosmic drumbeat, dictating how we see, how we measure, how we understand. And it carries with it the paradox of scale. On small scales, expansion does not rule. Your chair is not swelling beneath you. Your coffee cup is not stretching on the table. The atoms in your bones are not flying apart. Gravity, electromagnetism, and the strong forces of matter hold them fast. Even galaxies remain bound. The Milky Way will not expand into nothingness. But between clusters of galaxies, in the vast gulfs where gravity loosens its grip, expansion wins. There, distances lengthen, horizons drift away, and light itself stretches to breaking. In this picture, we begin to glimpse the full strangeness of existence. The universe is not static. It is restless. It grows. It carries us with it. And as we look outward, we are not just peering into space. We are peering into time, watching expansion itself, written in the language of light. The expansion keeps going, and stranger still, it is speeding up. When astronomers in the late 1990s used distant supernovae as cosmic mileposts, they expected to find a universe slowing under gravity's steady hand. Instead, they found acceleration. Something unseen was not only refusing to let expansion ease, it was turning the stretch into a quiet sprint. We now give that something a placeholder name: dark energy. It might be an intrinsic property of space itself, a kind of pressure woven into the vacuum. It might be a field we have not yet captured in our equations. Whatever it is, it dominates the cosmic ledger today, outweighing ordinary matter and dark matter in the grand budget of energy. If the universe began in a hot closeness, then bloomed into stars, planets, and lives, dark energy is the soft breeze that keeps the petals drifting apart. The image of rising bread still serves us well. The dough is not just rising, it is rising faster with time. There is no central oven, no preferred direction, only a steady, almost meditative swelling of the whole. It is strangely reassuring. Not a violent roaring, not the clatter of a runaway machine, but a patient widening. If space had a sound, perhaps it would be the quiet creak of a warm kitchen, an occasional pop of a bubble, the hush of something expanding, because that is simply what it does. So when we say the universe expands, we are not imagining galaxies shot from a cannon through a static void. The fabric itself stretches. Distances grow even when galaxies are not moving through space. That is part of why the discovery of acceleration felt both shocking and inevitable. The same geometry that lets space bend and ripple can also endow it with a pressure that urges it outward. Where gravity binds on small scales, dark energy encourages separation on the largest scales. Between those two influences, the cosmos finds its current rhythm. Sit with that for a moment. Every heartbeat you have ever felt, every memory on this small blue world, has unfolded on a pebble that spins inside a loaf of rising dough. The baker is not outside the oven. The oven is the universe itself. It makes you hungry for answers, but also for a midnight snack. Here is a rule physics keeps close. Nothing outruns light when it is moving through space. Not a rocket, not a signal, not even the cousin who boasts that he once outran 6 lanes of traffic. Einstein's relativity sets the speed of light as the universal speed limit for motion through spacetime. Yet at immense distances, astronomers see galaxies that appear to recede faster than light. Whole congregations of stars and dust sliding away at superluminal rates. Is the rule broken? No. The trick is that the rule governs motion through space, while the expansion changes space itself. Picture dots on a rubber sheet. Stretch the sheet, and every dot moves away from every other. Not because the dots crawl, but because the sheet grows. 2 widely separated dots can part at a rate that exceeds the speed of light, even though neither one is sprinting across the surface. Light still streams from one dot toward the other, but the fabric between them is lengthening, so the stream may never bridge the gap. Think of walking on a treadmill that quietly speeds up beneath your feet. You can walk toward a friend at the far end, yet the belt itself carries you both apart faster than you can close the distance. The problem is not your legs, it is the moving ground. The river image is useful too. Launch a small canoe upstream. If a sudden flood swells the current, the water flows faster than your paddling can compensate, and the boat recedes even as you strain. In our universe, photons are the paddlers, space is the river, and in far regions, the current wins. No law is violated because relativity restricts speeds through space-time, not the rate at which space-time can expand. We have seen this trick before in the earliest instant of history. Cosmologists call it inflation. A blink after the beginning, when space swelled at a staggering rate. In less than a heartbeat, measured in trillionths of a second, the universe leapt from subatomic smallness to something you could hold in your hands, if hands could hold space. Faster than light in terms of separation, yet never asking any particle to outrun a photon across the local fabric. Inflation ironed the wrinkles, smoothed the hot, lumpy newborn cosmos, and left behind a sky that looks remarkably uniform in every direction. Regions now widely separated once shared a neighborhood before the inflating river carried them apart. That early rush left fingerprints we can still read. It seeded tiny variations that would grow into galaxies and clusters. It also set the stage for the situation we live in now. Expansion persists. In the near reaches, gravity holds the Milky Way tight, and local groups of galaxies remain bound. Far out, where gravity loosens its grip, the current strengthens. There are galaxies we can see because their ancient light set out long ago when the river was slower. Their newer light, launched today, will never arrive. What we witness is like the fading red of taillights slipping around a distant corner. The glow still reaches us. The car is gone. There is a quiet sadness to that fact, and also a deep beauty. The universe contains more stories than we can ever receive. Some chapters are already unreadable to us, not for lack of patience or technology, but because information itself cannot cross the stretching road. Even so, look at what we have managed from our small vantage point. Photons from billions of years ago have landed in our telescopes. We have reconstructed how stars ignite, how galaxies assemble, how the background afterglow of the beginning still murmurs across the sky. From a modest star around the edge of a spiral, on a planet that holds oceans and people and sleep, we have learned that space can expand faster than light separates things, and that this is allowed because nothing is sprinting across the fabric. The fabric is doing the moving. All of this raises another question that tugs at intuition. What is the shape of the thing that stretches? Many imagine a giant black box, a room with edges, perhaps even with a border where a celestial sign reads, "Do not enter." Real space is subtler. It can be curved inward or outward, or it can be so gently flat that curvature hides beyond our best measurements. Geometry is not cosmetic. It guides trajectories, sculpts horizons, and whispers about the fate of everything. There are three simple possibilities to hold in the mind. One is flat space, like an infinite sheet. Here the schoolroom rules apply. Parallel lines never meet, and a straight path never loops back. Another is a closed space, the three-dimensional cousin of a sphere. Travel straight long enough, and you eventually circle back to where you began. The way a steady trek around Earth returns you to your starting point. The third is open space, curved like a saddle. Parallel lines peel away from each other, and triangles add to less than 180 degrees. In such a cosmos, straight lines never bring you home. You keep on slipping into the wide. Which one we inhabit depends on the total density of matter and energy relative to a critical value. More than critical bends space inward. Less than critical bends it outward. Exactly critical leaves it flat. Goldilocks becomes a cosmologist. To measure the balance, we read the ancient light of the cosmic microwave background. Its faint ripples carry information about how space bends light across vast distances. The pattern of tiny hot and cold spots tells us how the fabric is shaped. The answer so far is remarkable. Within the reach of our measurements, the universe looks very close to flat. Not necessarily perfect, but so nearly so that any curve must be gentle across the part we can see. Stand on a plane as wide as worlds, and it appears level to every horizon. That is our situation. Flat, does not decide the question of size. A flat universe can be infinite, or it can be finite, with a topology that loops in ways your intuition protests. Likewise, a closed universe can be finite, yet unbounded. That phrase sounds like a riddle until you recall the surface of a globe. The area is finite, yet there is no edge to fall from. Walk forever, and you never find a border. Translate that idea into 3 dimensions, and you have a space that encloses itself. No outer shell, no cliff, only a continuous fabric that returns to itself. Inside such a world, travelers who think they are heading straight might one day find themselves approaching familiar stars from the far side. Even in a flat or open case, an infinite expanse carries curiosities. With endless room, there are endless arrangements of matter. Given enough space, patterns repeat. Somewhere very far away, if infinity is real, there could be another listener, settled under a familiar night sky, hearing a familiar story, perhaps in different pajamas. It is a mathematical possibility, not a promise, and it is less important than the feeling it evokes, that we live inside a structure so large that even imagination must catch its breath. Curvature is not only a matter of shape, it affects destiny. In a closed cosmos where gravity one day overcomes expansion, everything might slow, halt, and reverse. That story ends in a great collapse, sometimes called a big crunch. In an open or perfectly flat cosmos, expansion can continue forever, thinning matter, cooling radiation, and stretching wavelengths into whisper. Dark energy shifts the balance even further. With a repulsive pressure that does not dilute as matter does, it steers the universe toward an ever faster drift. Under our current understanding, a big crunch looks unlikely. The more probable future is a long, gentle fade where clusters grow lonely and light reddens until even starlight becomes memory. Yet the word gentle hides a twist. The same acceleration that carries distant galaxies away more quickly also changes what we can hope to learn. Our observable bubble grows as ancient light completes its journey, but dark energy grows our isolation even faster. More and more regions slip beyond the event horizon, that cosmic shoreline beyond which new signals can never arrive. The particle horizon grants us a widening history book. The event horizon withdraws future pages before they can be delivered. The Museum of Light is both opening new halls and quietly closing others. Think again of Hubble's insight. Farther means faster. The proportionality captured in Hubble's law is not a single snapshot of recession, but a statement about the way the fabric scales distance into speed. Double the distance to a galaxy, and in a uniformly expanding universe, you double its recession speed. Add acceleration, and the proportionality evolves with time, but the intuition remains. Remoteness and retreat go hand in hand. That is why redshift becomes both a measure of distance and a measure of age. The longer the light has ridden the current, the more the river has stretched it. Inflation at the beginning and dark energy now are bookends of an odd symmetry. Both describe periods when the fabric's own energy drives separation. Both adjust what is possible to know. Inflation pushed once neighboring regions beyond causal contact almost immediately, then left behind a universe smooth enough for structure to grow. Dark energy, arriving to dominance late in the tale, does the opposite kind of editing. It takes regions that once could have communicated and ushers them across the horizon. It leaves us with a local archive of the early chapters, even as it denies us the incoming mail from far co-authors. The cosmos is generous with prologues and stingy with epilogues. We do not meet this with despair. We meet it with craft. We read the background afterglow, that faint microwave hush that fills all directions, and we extract the universe's composition from its tiny modeling. We use standard candles and rulers, supernova, and acoustic peaks to map distances as if the sky were gridded with survey markers. We weigh clusters by the way they lens background galaxies, their gravity bending light into arcs and smears. We inventory the invisible by its pull. In all of these methods, light is our courier. Its colors, its delays, its distortions, all become data. When space stretches those messages, we account for the stretch and still hear the meaning. Dark energy remains a riddle written in familiar handwriting. If it is vacuum energy, it should have a value far different from what we infer. If it is a field, we have yet to catch it in the act of changing with time. Observers continue to test for small deviations. Theorists continue to try new scripts. For now, we live with a placeholder that works astonishingly well. The models that include a simple cosmological constant, plus cold dark matter, plus ordinary matter and radiation, match the background glow, the distribution of galaxies, the late-time growth of structure, and the distances to supernova with a harmony that is hard to dismiss. The score is not perfect, but the notes ring true. What does this mean for us, on the scale of coffee cups and cities? Expansion does not pry the mug from your hand. Electromagnetism binds molecules. The strong force binds nuclei. Gravity binds planets to stars, stars to galaxies, and galaxies into local groups. Only across the vast emptiness between groups does the river of expansion run free. There, the metric itself changes with time. There, two unbound islands see their shorelines recede. Here at home, the waves lap quietly at the edge of our little archipelago, while the great ocean lifts its tide elsewhere. Still, we are not separate from the large. The atoms in your bones were forged in the cores of stars that lived and died long ago. Their light traveled in straight lines that were not straight lines at all, but geodesics drawn on a slightly curved map. Your thoughts, recorded in the firings of neurons, are carried by the same electroweak rules that govern the radiance of distant suns. When you look up, you are not outside the story. You are the story, wondering about itself. Let the mind return to shape for a last moment. Even if the global geometry is almost flat within what we can test, the topology can be playful. Space can tile itself in repeating patterns, can identify opposite faces of a fundamental cell so that journeys loop in subtle ways. In principle, with sharp enough eyes and a big enough sky, one could discover the same galaxy imprinted in different directions at different ages, like seeing a lighthouse twice in a fog by way of a mirror round a headland. We have searched for such signatures, and so far have found none. The sky appears to be free of obvious repeating motifs. The plain looks plain. Behind that result is a quiet satisfaction. The absence of odd echoes is itself a kind of map. As for destiny, the forecast under dark energy is a long evening. Star formation will dwindle as gas is used up or heated beyond utility. Existing stars will age, red giants will shed skins, white dwarfs will cool. The great clusters will thin into islands separated by gulfs that grow wider and darker with time. The cosmic microwave background, now a few degrees above absolute zero, will redshift until its wavelengths swell beyond any practical detector. History will remain, but its light will be stretched into silence. This could sound bleak. It need not be. Meaning does not require a crescendo. A story can resolve into quiet and still be whole. The wonder is not that everything lasts. It is that anything burns at all. Against a background that expands and a horizon that recedes, we are here. We can listen. We can read the letters in ancient light and recompose a tale that began before there were eyes to see it. We can place ourselves within it without being the center. Take one more breath and picture the sky. The galaxies we will never hear again are still there, and their last messages are still en route. And some of them will arrive tonight as a single photon that lands gently on a telescope mirror or on the back of your eye. That photon will be redder than when it left. It will be older than any mountain. It will have ridden a river that grew beneath it. It will carry news that is already out of date, and yet it will be exactly on time. The dough keeps rising. The oven keeps warming. The kitchen is larger than any house and is the house itself. In that kitchen, on a small table, someone sets down a mug and looks out a window at stars. The window is not the edge of the world. It is an opening into a fabric that has no border, where a border would make sense. Within that fabric, your life unfolds. Your thoughts join the background hum. The universe expands, and in the quiet, you can hear it. If space truly is flat, then we exist on a boundless plane of possibility. If it curves inward like a sphere, we might be looping around an invisible bubble, destined to meet ourselves again after an unimaginably long journey. And if it curves outward like a saddle, then we're forever sliding along a surface that diverges, heading into infinity with no return ticket. Each vision is elegant, strange, and beautifully perplexing, which is precisely what makes it magical. You don't have to pin down the geometry of the cosmos to appreciate its wonder. You can simply step outside on a clear night, gaze upward, and smile, knowing you stand on a tiny patch of something so immense and mysterious that even the best minds can only sketch it in metaphors. To begin grasping it, think of yourself as a small creature walking on the surface of a balloon. You can wander north, south, east, and west, but there's no digging beneath or floating above. That curved surface is your entire universe. Walk far enough in a straight line, and without ever turning, you find yourself back at the spot where you began. There's no edge, no border, only a seamless loop. The balloon's skin is finite, yet it feels infinite from the inside. That's the magic of curved space. It obeys rules that seem alien at first, but reveal a deeper harmony once you settle into them. Humans, of course, live in 3 dimensions, which complicates things. But curved, 2-dimensional surfaces, like spheres or saddles, give us a useful window into how the universe might behave on far larger scales. On a flat tabletop, geometry is simple. Triangles add to 180 degrees. Parallel lines never cross, and a straight path continues forever unless you bump into furniture. But shift onto a sphere, and geometry dances to a new rhythm. Draw a triangle from the equator to the North Pole and back again, and the angles add up to more than 180 degrees. Parallel lines that should march endlessly without meeting eventually converge at the poles. Walk straight and you'll circle back, never reaching a wall because there isn't one. It's a finite surface that masquerades as infinite to those confined to it. Now scale that idea up. Imagine that our universe is the 3-dimensional analog of a balloon surface, curving not in 2 dimensions, but in a way we can't directly picture, folded into higher dimensions invisible to us. We live inside this 3-dimensional space, moving through it just as the balloon creature moves across its curved skin. To us, the galaxies are like dots on that surface. As the balloon inflates, the dots drift farther apart, not because they crawl across the skin, but because the skin itself stretches beneath them. That's what cosmologists mean when they talk about cosmic expansion. Galaxies are not racing through empty space like cars on a highway. They are passengers, carried apart as the very road lengthens between them. And if the universe is truly finite and curved, then in theory, traveling straight long enough could bring you home again. Not back to your house, or your city, or even your galaxy, but to the very patch of space where you started, approached from the far side. There is no cliff edge to fall from, no wall marking the end. It loops gracefully upon itself, finite yet unbounded. You could take an infinite journey through a finite cosmos, and it would feel endless every step of the way. This balloon analogy also reminds us why there's no true center of the universe. On a balloon's surface, no point is the special origin of the expansion. As the balloon inflates, every dot recedes from every other. From the perspective of any one dot, it appears as though everything else is moving away, even though all are equal participants. The same is true in our universe. Expansion happens everywhere at once. From the Milky Way, it looks like all galaxies are retreating. From another galaxy, the same illusion holds true. Everywhere is here, and nowhere is the center. But the balloon metaphor is only a teaching tool. The real universe is not embedded in a larger container the way the balloon floats in air. Space doesn't require an outside to curve. It can bend and stretch entirely within itself, an intrinsic property described by Einstein's general relativity. Mass and energy tell space-time how to curve, and the curvature tells matter how to move. Planets orbit, stars congregate, and galaxies wheel in spirals because space-time is shaped by their mass, while their mass is in turn guided by space-time's shape. It is a conversation written into the structure of reality. The paths of light are equally dictated by this geometry. On a flat surface, light travels in what we call a straight line. But in a curved space, the straightest path is not what you expect. It follows geodesics, the shortest available routes, shaped by curvature. On Earth, those are great circles, which is why airplanes fly arcing routes that appear curved on a map, but are actually efficient on the globe. In the universe, light arcs around massive objects, bending like water flowing around stones in a stream. This is gravitational lensing, the funhouse mirror of the cosmos, stretching and magnifying galaxies, creating arcs of light across the sky. And unlike a carnival mirror, these distortions don't deceive us. They reveal truths about the invisible distribution of matter, including the mysterious dark matter we can't otherwise detect. When we peer into the sky, then, we aren't seeing objects sprinkled across a static void. We're witnessing light weaving its way through warped fabric, its path curved by the geometry of space. Each star and galaxy is a bead in an immense net, seen through the shifting lens of space-time. To the eye, it may seem serene, but hidden within is the constant ripple of curvature, the restless bending of light by the gravity of worlds. Return once more to the balloon. As it expands, the dots drift apart, but the dots themselves, the galaxies, don't grow. They stay bound by their own gravity. Our Milky Way isn't stretching like dough, nor is the solar system, nor your living room. Expansion acts only in the vast reaches between gravitationally bound structures. Galaxies and clusters are held together tightly enough to resist the cosmic stretching. But the gulfs between them grow wider, carried apart by the accelerating push of dark energy. It's as though the balloon is not just inflating, but inflating faster with every breath. We don't know what dark energy truly is. It could be vacuum energy, an inherent property of space, or a field we've yet to name. But we see its fingerprints everywhere. In the way supernovae appear dimmer than expected, in the way the cosmic microwave background's ripples spread, in the way galaxies accelerate outward. It's the breath in the balloon, the invisible hand coaxing the cosmos to swell more quickly with each passing epoch. So here we are, living inside a space that may curve, that may be finite yet boundless, expanding yet centerless. It is shaped by laws that defy daily intuition, yet flow with a kind of cosmic elegance once you surrender to their rhythm. The balloon is a humble toy, but it whispers ancient secrets. Next time you see one rising into the sky, think of it not only as helium and rubber, but as a metaphor for space itself, stretching within, not into something larger, but by its own nature. Each breath expands the whole, and each dot drifts apart. And just beyond this metaphor lies a concept that stirs both awe and unease: infinity. Say the word aloud, and it feels bottomless. Infinity is vastness without walls, a horizon that recedes no matter how far you chase it. It conjures stars without number, worlds without end, and paradoxes that can tangle the bravest minds. But what do we mean when we ask if the universe is infinite? Infinity, just saying the word, feels like standing on a cliff's edge, peering into a depth that has no bottom. It's a concept that humbles even the boldest thinkers, because it slips through the fingers of intuition. When we imagine infinity in the context of the universe, we conjure visions of endless stars and galaxies, stretching beyond every horizon, beyond every possibility of return. But infinity is not simply a matter of more distance, more space, more galaxies. It's a shift in perspective so profound that it changes how we think about existence itself. Let's begin with what we've been able to measure: the afterglow of the Big Bang. The cosmic microwave background is our best tool for taking the universe's temperature and geometry. Those faint ripples reveal that space is astonishingly close to flat, not bulging like a sphere, not sagging like a saddle, but almost perfectly straight in the mathematical sense. And in the framework of general relativity, if space is flat on large scales, then one likely possibility is that it's infinite. If it isn't truly infinite, then it must be so enormously large that the part we inhabit is indistinguishable from flatness. This brings us to the idea of the observable universe. Imagine a bubble about 93 billion light-years across. That's the sphere of everything we can see, the maximum reach of light that has had time to travel to us since the beginning. It feels impossibly vast, like a dream stretching out into the unknown, but it might be only the tiniest fraction of what really exists. Beyond that bubble, the universe may continue indefinitely, like a desert that stretches past every dune you can climb. We can't prove it. We can't disprove it. We are bound by the horizon of light, just as an ant on the beach sees only sand in all directions and can't know where the shoreline ends. And here's the catch: infinity can never be directly measured. It isn't a number to be added up or a distance you can cross. It's an idea, one that emerges when we test space for signs of looping or edges and find none. So far, every direction we've looked has yielded no wall, no sudden border, no warning sign telling us we've reached the end. The map keeps unfolding. Whether that map eventually loops in some higher dimension or stretches endlessly remains hidden beyond our reach. If the universe is infinite, though, the consequences are staggering. It would mean an unending quantity of matter and energy, a limitless field of stars and galaxies. Somewhere in those infinite stretches, there could be another world like Earth, perhaps with oceans a different shade, skies tinged in unfamiliar colors, trees branching in strange ways, perhaps even life, asking the same question we're asking now. Does space end? And the logic of probability stretches further still. In an infinite universe with matter spread roughly evenly, patterns would eventually repeat. That implies there could be another version of you, or countless versions, scattered across the infinite quilt of space. Some would be nearly identical, others wildly different. One might have chosen a different breakfast cereal this morning. Another might be listening to this story under a different sky. You won't ever meet them. They are separated by gulfs so vast that their light will never reach us. But mathematically, the possibility lingers. Infinity, then, is not only vastness, but inevitability. In a boundless cosmos, every arrangement of matter, no matter how improbable, must occur somewhere. That doesn't mean we should picture infinity as a collection of duplicates waiting to be discovered like a cosmic warehouse. Instead, it's a reminder that the familiar rules of finitude, edges, borders, endings, may not apply to the fabric we inhabit. But here's where caution enters. Scientists are careful not to declare the universe infinite without proof, because we only have one observable patch to work with. It's entirely possible that space is finite, but so large, so subtly curved, that we'll never notice the loop. Imagine standing in a meadow and insisting the earth is flat because you can't see the curve. The evidence in front of you is accurate, but incomplete. Infinity may be a mirage created by the limits of our perspective. Time complicates this picture too. Even if the universe extends endlessly in space, it still had a beginning, at least in the form we know it. Nearly 14 billion years ago, all of space and time as we understand them erupted into expansion. That suggests the cosmos, however large, is not eternal in the past. It may continue into the future indefinitely, but its age is finite. Infinity in one direction, finitude in another. A reminder that the universe is never as simple as our categories. Philosophers have long struggled with infinity. Aristotle rejected it outright, believing that actual infinities couldn't exist in nature. To him, infinity was a concept of potential, not reality. Even today, mathematicians treat infinity with care, distinguishing between different sizes of infinity in their equations, while physicists debate whether the universe can truly embody such an abstract idea. Some argue that infinities are signs of gaps in our theories, not features of reality. Others embrace them as possible truths. Regardless of which view proves right, contemplating infinity expands our imagination. It shifts the scale of our questions. Most of our lives are bounded by walls and clocks and fences. Infinity removes all of them, and what remains is possibility. A universe without edges forces us to abandon the idea of beyond. There is no outside of infinity, no final wall where it stops. If space is infinite, then existence is not a story written within borders, but an open-ended canvas. And yet, whether infinite or not, what matters most is that it is already more than enough. 93 billion light-years of observable cosmos is a feast too great to consume, a library too vast to finish. We don't need infinity to feel overwhelmed. We only need to stand under the night sky and let our eyes absorb the light of galaxies billions of years old. Already, we are immersed in a grandeur that defies our senses. Infinity, if real, is simply a further extension of that mystery. Still, The thought of an edge lingers. We're creatures of boundaries. We grow up with doors and sidewalks, boxes and borders. It feels natural to assume the universe must stop somewhere, like everything else we've ever known. The human mind craves an edge to peer over, a wall to climb, which is why the idea of a universe without an edge feels unsettling. Surely there must be a wall out there, a final limit beyond which there is nothing. But the universe seems to resist that narrative. It curves, loops, stretches, and expands, but so far, no wall has appeared. If there were an edge, what would it look like? Would it be a shimmering boundary where space ends and something else begins? Would you fall off, like the old myths of sailors sailing over the rim of the earth? Or would you simply bounce, unable to cross into non-existence? These questions expose how limited our intuition is. We try to picture absence, but absence has no picture. To imagine beyond the universe is to imagine nothingness, which our minds can't do. We can imagine empty space, but empty space is still something. Nothing is different. Nothing has no dimension, no time, no possibility of observation. So maybe the better way to think of it is not as a wall, but as a kind of boundary written into the rules of reality. Space may be finite, but unbounded, like the surface of the earth. You can keep walking forever, but you never leave the surface. The journey has no end, even though the area is finite. Apply that concept to 3 dimensions, and you begin to see how the universe might be both limited and endless in different senses. Whichever possibility turns out to be true, infinite expanse or finite loop, the lesson remains the same. We are creatures standing within something greater than we can ever fully know. The horizon of knowledge recedes as quickly as we chase it. There is humility in that, and also peace. You don't need to know whether space is infinite to appreciate its wonder. The mystery itself is enough. So the next time you look up at the stars, let the question linger without seeking to resolve it. Is space infinite? Perhaps. Is it finite? Perhaps. Either way, you're already part of it, woven into its fabric, a brief spark in a cosmos too vast for certainty. And whether the journey leads back to where you began, or stretches on without end, you are walking it now. That in itself is extraordinary. It feels natural to imagine that after some unimaginable distance, the universe must present a final hallway, a last door, an edge like the lip of a vast tabletop, hanging above an abyss. Yet space does not require edges. It can be finite in size, without any boundary at all, which is where the story turns beautifully strange. Think first of Earth's surface. Walk in a straight line long enough, over sea and ice and continents, and you'll find yourself right back where you started, and you return to your starting point without ever encountering a wall or a cliff labeled end of planet. The surface is finite, yet unbounded. No edge is needed, only curvature that brings a path back upon itself. Now lift that idea into 3 dimensions. Picture a volume that wraps around itself the way a sphere's surface wraps in 2. Travel in a perfectly straight line, avoiding stars and dust and all the minor dramas of matter. And after a very long time, you arrive where you began, without ever striking a border. That is a perfectly respectable geometric space. Cosmologists call this a finite, unbounded space. The phrase sounds like a contradiction until the geometry clicks. A space can be complete and self-contained without an outer rim or an outside at all. To visualize, people often borrow the torus, not the jelly-filled pastry with powdered sugar, but the smooth donut with a circular hole. The donut surface is finite and unbounded, and it loops in two independent directions at once. Imagine being an ant on that surface. Walk east forever, you circle around. Walk north forever, you circle around. There is no edge to fall from, no fence to halt you. Extend this looping idea into three-dimensional volume, and you have a space that can close upon itself in subtle ways. A kind of multi-direction wrap that returns straight-line journeys to their origin after stupendous distances. Classic arcade games offer another helpful picture. In some versions of Pac-Man or Asteroids, leave the screen at the right, and you reappear on the left. Slip out at the top, and you drop in at the bottom. The playing field is finite, yet the edges connect rather than block. That is a two-dimensional echo of a toroidal topology. In cosmology, similar identifications can be done in three dimensions, producing a compact space that is large but edgeless. You can live your entire life inside such a world and never find a border, because there is none to find. Is this merely metaphor? Not entirely. Some cosmological models allow the universe to have such a looping topology. If the loops were small enough on the largest scales, we could in principle detect them as repeated patterns in the sky. For example, the earliest light we can see, the cosmic microwave background, might contain mirrored or repeating signatures, like faint wallpaper patterns left by the geometry of space. Observers have searched for these echoes. So far, the evidence suggests that if loops exist, they are larger than our observable bubble. But the door remains slightly ajar. The absence of obvious repetition does not prove infinity. It only tells us that any global looping is too large or too subtle for current maps to reveal. The deeper reason edges are unnecessary is that space is not a thing sitting inside a larger thing. Space is the arena itself. There is no need to embed it within a surrounding container. Curvature is intrinsic, which means the fabric bends by its own rules without leaning on a higher dimensional scaffolding we can access. We can describe that curvature entirely from measurements done inside the space, by tracing geodesics, by following how light deflects near mass, by watching triangles refuse to sum to the schoolroom 180 degrees. Nothing about those measurements requires a wall where space stops. The geometry can close upon itself smoothly, and if it does not close, it can still extend without limit. What if space truly were infinite? Then there is no edge by definition. Infinity is not a place where you can plant a flag. It is a property of unending extension. You do not need to find the last number to be convinced that numbers do not end. Likewise, you do not need to discover a rim in order to accept that space may have none. Infinity raises its own curiosities. An infinite cosmos likely contains an unbounded tally of stars and planets, perhaps innumerable pockets where chemistry knits itself into life. Given enough volume and an approximately uniform distribution of matter, arrangements repeat. Far beyond all hope of contact, there could be regions where patterns rhyme with our own, familiar in outline, yet altered in detail. This is not a promise of doppelgangers at the grocery store. It is a reminder that probability, given endless room, will eventually sample every possibility you do not forbid. The human mind prefers edges. Containers make sense to us because our days are defined by rooms and fences, by streets and doorways and boxes with lids. That preference becomes a trap when we try to scale it to the universe. Suppose you insist that space must end. Then you face the question, end into what? If beyond the edge there is more space, then you have not found an end. If beyond the edge there is truly nothing, not vacuum, not dark matter, not time, just nothing, then even the word beyond collapses, because nothing does not permit direction, or distance, or duration. Our language tries to paint a picture of absence, but absence has no picture. When philosophy walks to the cliff, physics quietly turns back to geometry and says, "Let us test the shape from the inside." Time adds its own kind of boundary. Space may be edgeless, yet our universe has a beginning, in the sense that the hot, dense state we call the Big Bang marks the earliest moment our current description can reach. That is not a location in space. It is a moment in cosmic time when the entire fabric was hotter, denser, and opaque to light. Asking what came before is like asking what lies north of the North Pole. The question points past the end of our coordinate chart. Perhaps a deeper theory will extend the map. For now, the boundary we face in the past is not a wall in space, but a limit of description. All of this gives the universe a different feel than a box with a lid. It is less like a container and more like a melody that continues, a structure defined by relations rather than edges. Gravity couples to mass, light follows the curves, motion traces the geodesics, time measures change in the fabric. Whether the global shape loops upon itself or stretches without end, what we experience are connections rather than borders. If you imagine a starship streaking toward a supposed rim, the truer picture is a long, quiet voyage that never finds a cliff. Only more night, more whispers of ancient light, more questions. Before stars existed, before galaxies settled their spirals, before atoms could calmly hold electrons, there was a glow. It was soft and uniform, a fog of light filling everything. Not a flash, not fireworks. More like dawn's first diffuse brightness sliding under a door. Some of that glow persists now. We call it the cosmic microwave background. It is the oldest light anyone can see, a whisper from when the universe was not yet 500,000 years old. It bathes the sky at microwave wavelengths, passing through you and me in this moment, a faint warmth from the beginning. To grasp its origin, roll time back to the hot, dense early cosmos. At first, the universe was a blinding plasma, a seething soup of free electrons and protons with photons ricocheting constantly. Light could not travel far without being scattered. The cosmos was opaque, like trying to shine a flashlight through milk. As expansion proceeded, the temperature dropped. After roughly 380,000 years, electrons and protons combined to make neutral hydrogen. With the free charges gone, photons no longer scattered incessantly. The fog lifted. Light decoupled and began traveling freely. The first clear photograph was taken, so to speak, and the subject was the universe itself. That radiant image has been stretched by expansion from blazing ultraviolet to gentle microwave. It fills the sky almost uniformly. Almost. When satellites like Kobe, WAMAP, and Planck mapped it with exquisite care, they found tiny ripples in temperature and brightness, differences of a few parts in 100,000. Those faint mottlings are everything. They are the seeds from which structure grew. Regions a hair denser drew in matter a little faster, and over billions of years, those slight preferences amplified into stars and galaxies and clusters. The pattern is a blueprint of destiny. It is also a ruler and a protractor. The size and distribution of those ripples carry information about the composition of the universe and the curvature of space. If the fabric were strongly curved inward or outward, the hot and cold patches would appear warped in characteristic ways. Instead, within our observational limits, the pattern fits a cosmos that is very close to flat. Not necessarily perfectly flat, but flat enough that any global bend hides beyond our horizon. Light becomes data, and data becomes geometry. We read the oldest glow to learn the shape and the ingredients of everything around us. There is something soothing in the idea that this quiet background is always present, not visible to your eyes, but always there, a faint radio hush. The universe's baby photo, still on the wall, still legible after all these years. You do not need to chase the edge to meet the beginning. The beginning is already arriving, everywhere, as a soft afterlight. We circle back to edges because the thought refuses to let go. If the mainstream picture points to a cosmos without a hard rim, could boundaries exist in stranger forms, hidden from ordinary sight? Some speculative ideas say yes, cautiously. Consider brain cosmology, which arises from certain versions of string theory. In this picture, our observable universe could be a three-dimensional membrane, a brain, embedded in a higher dimensional expanse, sometimes called the bulk. All familiar particles and forces, aside from gravity, would be confined to this brain, like dust stuck on the surface of a soap bubble. Gravity might leak into the extra dimensions, which could help explain why it seems so weak compared with electromagnetism or the strong force. If such a model were correct, there might be a sense in which our brain has a boundary within the larger bulk, even if inside our three-dimensional world everything looks continuous and edgeless. A hypothetical five-dimensional observer might see our universe as a finite object with a rim. From our perspective, we would never encounter that rim, because motion off the brain is not among our allowed directions. We would live our entire history inside a seamless volume that presents no borders to inhabitants like us. The edge would exist in an external sense we cannot access, the way a fish in a lake cannot walk on the shore. Another speculative possibility involves domain walls, which are boundaries between regions that settled into different physical states during symmetry breaking in the early universe. Think of water freezing into ice, but choosing different crystal orientations in different places. Where the orientations meet, a line or a wall forms. Translated into cosmology, if the infant universe fell into slightly different vacuum states in separate domains, interfaces might remain between them. These domain walls would be genuine physical structures, and across them, certain properties could change. Perhaps the masses of particles by a tiny amount, perhaps the strengths of interactions by a whisper. We do not see such walls in our observable patch, which either means they do not exist here, or they formed in ways that left us inside a single domain. Still, the idea reminds us that boundaries, if they exist, need not be geometric edges where space stalks. They could be transitions where the rules shift. More radical suggestions appear in multiverse scenarios, where what we call the universe is only one bubble among many in a larger inflating sea. In such pictures, bubbles can, in principle, collide, leaving rings or scars in the microwave background. Searches for those signatures have not yielded convincing evidence. That does not end the speculation. It only emphasizes our current horizon. Even if other bubbles exist, their light may never reach us. The multiverse could be vast beyond stories, while our observational universe remains its own quiet chamber. It helps to notice a pattern. Whenever we press for edges, the answers return to horizons and to what information can reach us. The particle horizon marks how far light has traveled since the beginning. The event horizon marks the distance beyond which new messages can never catch up, because expansion carries the senders away too quickly. These horizons are not walls in space. They are limits of communication written in time. They shift as the universe ages, and under the influence of dark energy, the communication limit grows more severe in the deep future. Many distant galaxies that we see now will fade from view forever, not because they disappear, but because their new light will never arrive. The map shrinks in what it can add, even while the Museum of Ancient Light grows richer as long-traveling photons complete their journeys. If space has no edge, what holds it together? The question itself imports the wrong picture. Nothing needs to hold space the way a rack holds plates. The fabric is described by equations that determine how it evolves. Those equations connect curvature with energy and momentum. In practice, when we ask what the universe is made of, we tally energy densities, ordinary matter that makes stars and you and me. Dark matter that reveals itself through gravity. Dark energy that steers the late-time expansion. Radiation that grows ever thinner and cooler as it redshifts. The geometry follows from the balance. The balance follows from the history. No rim is required, only laws that speak softly but never cease. Return for a moment to finite, unbounded spaces. Suppose the global topology does loop. Could we ever notice, in principle, if the fundamental domain were not too large, we might see multiple images of the same distant galaxy, appearing in different directions at different ages, like a lighthouse glimpsed twice around a headland by way of a mirrored bay. We have looked for these ghostly repetitions and found none that convince. That negative result tells us that if a loop exists, the scale of the loop exceeds the radius of our observable universe, or the pattern is too subtle to register. The plainness of the sky is a result as meaningful as a pattern would have been. Sometimes absence is a clue. The cosmic microwave background is again our best surveyor. Its tiny ripples encode sound waves that rang in the early plasma, and their measured sizes give us standard rulers. The locations of the peaks in its power spectrum tell us how far those sound waves traveled before recombination, then stretched by expansion. From those rulers, we infer distances and curvature. From the overall fit, we infer the composition. The data point toward a universe that is very close to flat, with dark energy in the lead today, dark matter next, and ordinary matter trailing far behind. This is not a vote for infinity, but it is consistent with it. It is also consistent with an edgeless space that is finite on scales larger than our horizon. The map is generous in what it allows, conservative in what it confirms. Edges also tempt us because of narrative. Stories begin, rise, and end. A box closes, a curtain falls. We like endings because we are given endings in our own lives. The universe may be offering a different kind of tale, one that resolves toward quiet rather than closure. Acceleration will slow the conversation between distant structures until the loud chorus of galaxies thins to a few local voices. Star formation will dwindle. The glow of the background will stretch beyond practical detection. The archive will remain, but the delivery of new messages will cease. It is not a cliff. It is an evening. If that feels melancholic, shift the angle. The fact that there is no edge to find means you do not have to go anywhere else to be at the heart of the cosmos. Wherever you stand is as central as anywhere. The same laws apply. The same background surrounds you. You are inside the melody, not listening through a door. The edge you thought you needed was a reflection of the boxes you know. The universe prefers relations to rims. So if you ever picture a brave ship aimed at the end of everything, imagine instead a long, patient voyage that always discovers more night ahead, more starlight arriving late from places now beyond reach, more background warmth whispering of a time when the whole sky was a fog. The ship never finds a final wall, not because the universe stretches forever, necessarily, but because space does not need an end in order to be complete. A finite unbounded space would return the ship by a great circle. An infinite space would never run out of path. In either case, the lesson is the same. There is no cliff to fall from, only a fabric to wander. And in the wandering, the evidence gathers. Photons that left when the universe was young arrive tonight at a detector on a mountaintop or at the back of your eye. They have been stretched by a history that refused to rush, and they tell you about a world without edges in all the ways that matter. They tell you about curvature without a container, about beginnings that live in time rather than space, about a glow that never stopped traveling. Listen long enough, and you will hear the shape of the universe in the way light was braided on its journey. You will hear that the story continues whether or not it loops, that it does not require a border to be whole. You can close your eyes and picture none of this with perfect clarity, and that is fine. The point is not to solve the entire geometry before sleep. The point is to feel the quiet of a cosmos that does not end in a cliff face. You are already inside its completeness. The night is not a wall, it is a pathway. The horizon is not an edge, it is a limit that moves with time. Breathe and let the question rest where it belongs, not as a problem to conquer, but as a wonder to carry. Cosmologists have long wondered whether the universe has edges or strange boundaries. Several speculative ideas explore possibilities beyond our normal sense of space. One such concept is domain walls. In the very early universe, different regions might have frozen into slightly different physical states during symmetry breaking. The borders between these patches would form walls stretching across space. In most models, they would have vanished quickly, but some theories imagine they could still exist. Passing through one might subtly change physics. Your atoms could act differently, or even your tea might taste odd. Another possibility is that our universe itself is a bubble born from cosmic inflation. Inflation suggests that quantum fluctuations created many bubbles, each with its own physical properties, different constants, different strengths of forces, even different numbers of dimensions. This scenario, called eternal inflation, naturally leads to the idea of a multiverse, where countless bubbles form a cosmic foam. Our bubble might never meet another, since distances are vast, but collisions could, in theory, happen. Though rare, such collisions might leave detectable imprints. While highly speculative, the bubble model paints a poetic picture of a universe as part of a foamy sea of realities. Even more exotic is Gödel's rotating universe, a mathematical solution from Kurt Gödel in 1949. He imagined a cosmos not expanding, but rotating as a whole. In this strange geometry, time itself loops, making closed time-like curves possible, meaning you could theoretically return to your own past. It isn't physically realistic, since our universe doesn't rotate that way, but the model is valuable for showing how Einstein's equations allow possibilities stranger than fiction. Instead of edges, it blurs the line between boundaries of space and boundaries of cause and effect. Another radical proposal is the holographic principle. Here, our three-dimensional reality may be encoded on a two-dimensional boundary, much like a hologram stores a full image on a flat surface. This isn't science fiction projection, but a mathematical idea rooted in string theory and black hole physics. If true, the edge of our universe might not be a wall, but a boundary where information is stored. It suggests that our perception of volume could emerge from a deeper informational surface. The lesson behind these models isn't that we'll find a wall with a do not cross sign at the end of space. Instead, boundaries might exist in forms we don't expect, as changes in physics, shifts in curvature, or deeper informational structures. The cosmos may have no edge in the conventional sense, yet still confront us with limits. The limits of what we can observe, what our equations describe, or what our instruments can measure. Those limits are boundaries too, even if they aren't physical walls. Because humans evolved in rooms, landscapes, and boxes, we instinctively search for edges. But the universe does not owe us a boundary. It could loop inward, stretch infinitely, perch as a bubble in higher dimensions, or take some form beyond imagination. What matters is that we inhabit it, asking questions from within. The real edges may be at the boundary of knowledge rather than the boundary of space. These reflections naturally lead to the multiverse hypothesis, one of the boldest ideas in modern physics. The multiverse suggests there may be more than one universe, perhaps infinitely many, with different particles, laws, or dimensions. Some might be too alien to sustain matter. Others could support alternate versions of familiar worlds. Despite their appeal, these multiverse theories face criticism. The biggest challenge is falsifiability. If other universes are forever beyond reach, how can we study them? Without testable predictions, some argue the multiverse risks drifting into philosophy rather than physics. Others counter that it can help explain why our universe's constants seem finely tuned for life. If countless universes exist with different parameters, it's not surprising we happen to live in one where conditions permit existence. Some cosmologists even speculate that indirect evidence could emerge, such as unusual patterns in the cosmic microwave background caused by bubble collisions. But so far, no convincing signals have been found. For now, the multiverse remains speculative, yet stimulating, encouraging us to stretch imagination and remain humble about our place in the cosmos. Even if these ideas remain unproven, they enrich science by expanding the questions we ask. Science is not just about answers, but about enlarging the space of wonder. Whether or not other universes exist, pondering them reminds us how vast, strange, and surprising reality can be. The chapter circles back to the original question, where does space stop? After exploring bubbles, brains, holograms, and multiverses, the answer is still uncertain. Space may not stop at all. It may be infinite, finite but unbounded, looping in ways we can't perceive, or nested within something else entirely. What we do know is that space is dynamic and alive, expanding, curving, filled with galaxies and cosmic backgrounds, carrying the hum of the Big Bang. It has horizons, the observable limit of what light has reached us. But beyond that horizon, mystery persists. Perhaps the most meaningful conclusion is that the universe doesn't need an edge to be complete. Its wonder lies not only in what we know, but in what we cannot yet know. The absence of a clear boundary is not a failure, but an invitation to keep observing, keep questioning, and keep letting curiosity Stretch as far as imagination allows. In the end, maybe space never stops, not necessarily because it is infinite in extent, but because it is infinite in mystery. Its true edges might be where our questions end, not where space ends. And perhaps that is the greatest gift of all, a cosmos that invites wonder without walls.